Alright, today we're going to be talking about exponential decay. We previously learned about what exponential growth is, and that's an increasing exponential function. Exponential decay is just a decreasing exponential function. For example, if we were to graph a exponential decay, it would probably look something like this, where it was decreasing. Okay, whereas a growth, an exponential growth, would be like that. All right. So, if you recall from before, an exponential function is a function in the form of f of x equals a times b to the x, where a is a non-zero constant, or our beginning, and b is greater than 0 and not equal to 1, and x is any real number. Okay? If b is greater than 1, then it is an increasing exponential function. If it is less than 1, then it is a decreasing exponential function. All right, so going over our formulas for exponential decay and breaking them down, we are still using this function y equals a times b to the x. And we're going to talk about a is our starting amount, b is our base, which is between 0 and 1, and that's the decay factor. So for example, if I had it was decreasing by 4%. My base would be 100% minus that 4% to get me 96%, which I could turn into 0.96. Which, if you notice, is different than when we have an exponential growth, because normally we were adding 100% plus the 4%. In this case, we're subtracting because it's a decay, right? And x is the exponent, and in this particular case, usually it has to do with time. All right. So it's good to be able to spot the difference between an exponential decay and an exponential growth. So we're just going to go through that real quick. So determine whether the following functions model exponential growth or exponential decay. So what you're looking at is the base number. And from there you can figure it out whether or not it's an exponential growth or decay. In this case, because it's over 1, it's a growth. Because this is less than 1, it's a decay. So what I'd like you to do tonight in your whisk is actually do these two problems for me. Tell me whether or not they are exponential growths or exponential decays. All right, now, the big scary part, the word problem. So, in order to use this formula, we usually use it with word problems. So I have this problem here. It says since 1980, the number of gallons of whole milk each person in the U.S. drinks each year has decreased 4.1% each year. In 1980, each person drank an average of 16.5 gallons of whole milk per year. What is the approximate consumption per person of whole milk in 2000? All right. So we need to figure out, we have our formula y equals a times b to the x power. So I need to just figure out the parts here. So I have y equals, well, what's my initial amount? It says in 1980, each person drank an average of 16.5 gallons of whole milk per year. So in this case, the 16.5 is going to be my base number. Multiply that by However, it's increasing or decreasing. In this case, when you read the problem, it should be fairly obvious that this is a exponential decay. It says it right in the problem. Each year it has decreased. Important word here. 4.1%. So in this case, I'm going to need to take my 100%, subtract it by 4.1. All right, and I'm going to get 95.9%. From here, I'm going to turn this into a decimal in order to put it into my formula. So I'm going to turn it into 0.959 and then put that to the power of however many years. Well, we have to figure out what's the time lapse between our beginning time in 1980 and what we're trying to figure out now, which is in 2000, 20 years. So you put that to an exponent of 20 years. All right, so after doing some calculations and plugging this into your computer, you're going to get approximately 7.1. All right, so what that's telling us is that the approximate consumption per person of whole milk in 2001 is 7.1 gallons of milk. All right, easy enough. Easy enough. Let me know if you have any questions or concerns. Otherwise, just do those two other problems in the WIS tonight, and I will look at them tomorrow. Have a good evening.